So we toss a two-sided fair coin 3 times, okay? Let's say we decide to do that. Well, we could list all the outcomes, right? To do that efficiently, we could use a tree diagram. That's what I'm doing here. So this is the first toss, heads or tails. The next row underneath, so to say, would be the second toss, heads or tails from here, heads or tails from here, right? And then finally, we toss it a third time, so we get heads or tails from each outcome. See? All together then, right? How many possibilities are there? Well, we count the branches at the very bottom. Remember, it's like an upside down tree, so to say, and this is driving me nuts. Let me just, sorry, this was out of place a bit. I just wanted to move it up. Okay, I feel better now. So we have 1, 2, 3, 4. Wait, what am I doing? Here we go. 1, 2, 3, 4, 5, 6, 7, 8. So we know there are 8 possibilities, but what are they? You start at the top and get to the bottom. So this would be one outcome, all heads. Another one would be head, tails. Another one, tails, heads. Another one would be heads, tails, and so on. I have them all listed here actually already, which is nice. But that's how you would get all the outcomes. Okay, that's good. Well, let's use this. Let's now find some probability. Let's find the probability that the coin lands heads up exactly 3 times. And let's also find the probability that the coin lands heads up at least once. Okay, well, we saw the sample space, right? Here. How many outcomes are there where the coin lands heads up exactly 3 times? There's only one, right? Here. That's the only outcome. That's the only outcome where the coin lands heads up exactly 3 times. So that probability is 1 out of 8. For the second event, that the coin lands heads up at least once. So the coin lands heads up at least once. Well, that's basically the event was there. But if we just even look at the sample space, every outcome except one has heads in it. Meaning 7 out of 8 outcomes correspond to the event we're interested in. I mean, the event is actually listed here, but I wanted to show you how we got it from the sample space. So the probability is 7 out of 8, 7 over 8. Okay. So again, the coin lands heads up at least one, so every outcome has at least one head in it, at least one H, that is. So there are 7 out of 8. So the probability is 7 out of 8. Okay, so that's using the sample space. Let's use this formula just to illustrate it. Well, the probability of the coin landing heads up at least once, from the formula, that would be 1 minus the probability that the coin never lands heads up. So the event would be that the event happening at least once would be the coin landing heads up. So the probability of the coin landing heads up at least once, heads up would be the event, so to say. Never landing heads up, well, what's the probability that the coin never lands heads up? Well, if we did go back to the sample space, there's only one outcome, right? Where the coin never lands heads up. There's only one, all tails, so 1 out of 8. The probability of the coin never landing heads up is 1 out of 8, right? So therefore, again, we're just verifying the formula, at least with this example. The probability that the coin lands heads up at least once, right? That would be 1 minus 1 over 8, which by basic wonderful fractions is 7 out of 8. Okay? Isn't that, okay, so that's cool. So again, I'm just illustrating the formula. I mean, obviously, it's not a proof, but, just illustrates the formula. Does this make sense? I mean, sorry, let me ask this. Do you have any questions about this? Really hope this makes sense. Okay, let's keep going then. Okay, so if we go back to our earlier example with the passwords, right? Okay, so we have the formula, of course, right? So let's find the probability of choosing a password where no character was repeated. Okay, so if we want the probability of that in the password we choose, right? No character is repeated at all. Okay. No, excuse me. That's not. Wait. I think I made a mistake here. That should be at least once. I'll come back to that another time. Okay. I think I made a mistake on that slide, on this slide. So I'm going to skip this. Okay. I think it actually should be the probability of choosing a password where at least one character is repeated. That's what I meant to write. So, okay, I'm going to skip this slide. Sorry about that. All right. Let me just delete it. Sorry about that. Now we're in combinations. So here, now the question is, all right, well, what if order did not matter? Okay. What if order did not matter and we're choosing without replacement? Okay. So the order does not matter. Selection, however, is made without replacement. Well, in this case, we're not going to have permutations, right? Because permutations, right? That's where the order does matter. Here, the order does not matter. Here, we're going to have what's called a combination. Okay, a combination. With a combination, again, this is when you have n possible items, right? You want to make an arrangement of r of them, of size r, in other words, without replacement, meaning no repetition, and order does not matter. Well, here we have a combination, and it turns out the number of possible combinations then, C of n r, again, the book C of n r, excuse me, turns out to equal this. Okay, turns out to equal this. Okay, now you could again go by this formula if you wanted to. Desmos does have notation. Instead of a P, basically it's a C. So instead of NPR, it'd be NCR, excuse me. I mean, the only real difference here is that you're dividing by R factorial, which is P of RR. And you're dividing by that because you have to account for the fact that order does not make a difference. So that happens with a combination. Okay. So again, you could go by this formula if you wanted to. You don't have to though, because, excuse me, Desmos has NCR in it. Okay. Good. Okay. Excuse me. So let's do an example of that. Suppose we're at a charity event, okay? 30 people are there. They're giving away 3 $100 prizes as door prizes. So, what they're going to do, I guess, is maybe they have everyone's name. They're going to reach into, somehow they're going to call the names of 3 individuals at random. Somehow they're going to do that. Nobody can receive more than 1 prize, though, okay? But how many ways can the prizes be awarded? Well, notice that the order in which they call the people does not make a difference, right? Because they're all winning the same amount of money. It's not like one person's going to get $300, another person's going to get $200, and a third person gets $100. It's not like that. The order doesn't make a difference here. If we're there at the party and they call me first, or they call me second, doesn't matter. I win the same amount of money. Also, again, there's no repetition. And why is that? Nobody can receive more than one prize. So once they call a person's name, they can't be called again. Well, here you're basically dealing with combinations, right? In this case, there are 30 people, and you're choosing 3 of them. So we have NCR, we have C of 30, 3, which is equal to, by our formula, this. Okay? Which is also, if you were to work it out, right? You actually, if you were to work it out, you would get the stuff on the right, this stuff. I mean, the top here, I'm just using something we saw earlier. N factorial is n times n minus 1 factorial. So, but again, you can get this using Desmos. Let me show you. Just fix that. Wait, actually, let me share Desmos for you. See wait till it comes up. Okay, good. Now you can see it. Like, you go to Math Tools. You don't have to be logged in, but you can. You go to Scientific Calculator, as you can see. So if you go to where you found NPR, that's under FUNC for function. Here's NCR, okay? So if we did 30, 3, as you can see, we get the same amount, which is 4,060. Again, order doesn't matter here.